But since, I was not expecting a so big audience, and so I think there is a lot of people that didn't follow the previous talk that I gave last time. So do not hesitate to ask if there is things that are not known and not. First I will recall some definition. And reminders, maybe not reminders for everyone. So first of all, what is an orbifold? So here I will have to be slightly more precise than last time. So n-dimensional orbifold is a paracompact complex space on X such that for both X inside X, so the idea is that we only have quotients like this. So for me, I consider orbifold here as complex space. So it's not a stack vision of orbifold, but we need that locally the singularities are always quotient singularities. Okay, so how we will formalize this? We will formalize this as follows. So for the X, there exists a neighborhood of X inside X. There exists this neighborhood will looks like a quotient. So we'll have a quotient by an open in Cn. Take an open in Cn. We consider a group, an automorphism group of V, finite. And then we have the map P, which is just more or less a quotient map. So from V to V quotiented by J, and an isomorphism P. So this is for each X there exists this force. Okay, and this data, so U, V, J, and Pi, this data will be called this quadruple is called a local information system. System of X. Okay. But for short, this is very long, so local information system. But for short, I will call it LUS. Okay. So this is and so in the title there is primitively symplectic orbifold. So I explain you what is an orbifold. Now I will explain what is a primitively symplectic orbifold. So that's one definition. And then I will explain why we are studying this kind of object. What are the motivations of this kind of object? So a Kähler compact orbifold X is called a primitively symplectic orbifold. So there is two conditions. So first condition, we have an holomorphic 2 form. So there is, if I take holomorphic 2 form of the regular part of X, so there is a unique holomorphic 2 form, and this form is non-degenerate. So it's a symplectic holomorphic form. So this is the first condition, and the second condition is more technical. It's that the codimension of the singularities of X is bigger or equal to 4. So okay, maybe now I can give a little bit of motivation. So this is a generalization of what is called hyperkähler manifold. So I don't know if everyone is already heard about this. So in the generalization, it's a generalization with singularities. Okay, so orbifold can have some singularities, so quotient singularities. So yeah. And why we are studying this kind of object? Actually, it's for classifying varieties. So these are the elementary bricks to classify more complicated varieties. There is the Bogomolov decomposition theorem. I don't know if everybody knows about that, so I can record it.
So you mean it's non-degenerate over all the regular part?
Exactly. Okay, so yeah, I don't know if Bogomolov decomposition theorem is known, so I can recall it. So there is a generalization, recent generalization actually of the Bogomolov decomposition theorem by many people in the singular case. So I will explain. So from a lot of people, there is Greg, Québecus, Peternel, Euring, Len, and Genancia. Many people. So you take, let X be a Kähler variety with a trivial divergent class. Then there exists an quasi-eta cover. Quasi-eta cover. Such that X still decomposed as follows. So it will be a torus times what we can, some Caladio orbifolds, Caladio manifold varieties, and some hyperkähler, irreducible symplectic varieties. So this is Caladio, and this is irreducible symplectic. Okay. Yeah, so irreducible symplectic varieties, it's just a little bit more specific than primitively symplectic varieties. I don't want to really give too much detail about that, it's just to explain you the motivation, to see if we are able to understand these varieties, we are able to understand if we are able to understand the Caladio and the irreducible symplectic, we are able to understand the whole varieties with Gaussian class equal to 0. Actually, also the Kähler varieties, there is a way, well, it's still conjectural, but to decompose it. And one of the in this decomposition, one of the class will be the one with C1 equal to 0. So the goal of all of this is to classify all the Kähler varieties. Study Kähler varieties.
The codimension that you put there, it's real codimention.
No, complex.
So for this theorem, is X smooth or what are the
Yeah,
singularities?
it's not smooth. It's not smooth. Not necessarily smooth. What are the singularities? I don't remember precisely. Sorry. I forgot. I was not expecting to speak about that. I was expecting a more local audience. But yeah, for example, orbifold singularities, it's work. It's work for orbifold singularities. You mean that the singularity is not too bad, but it's still very general. So I think at least it's normal. Maybe I don't want to say stupid things. I'm not fully sure.
Why do you call this primitively? Why the primitive?
Primitively, it's because we have only one holomorphic to form. So it's not only symplectic. Symplectic, we could have several holomorphic to form, and primitively, it's because yeah, and this condition, it's natural because I will explain why this condition is natural. Sorry.
It seems strong to me, that's why I asked.
Actually, it's not strong. It's not strong at all. I will explain why it's not strong and it's very natural. Maybe, yeah. Another motivation that I should speak about is the minimal model program. So the minimal model program is the objective of the minimal model program. It's to classify again the varieties by trying to find the simplest irrational model for varieties. And in this process, we found varieties that have singularities. And the one with first chain class equal to 0 play an important role for this another motivation for studying this orbifolds. So now I will just give some example and I will explain in the same way. We do the two things in one step, explaining why this condition is not a problem and why I'm giving some examples. So examples. So last time that I provided a technique to construct examples, so it's called the Fuji key construction. So I start with a K3 surface. And G. So a K3 surface is primitive symplectic. Smooth. The easiest is okay. G, finite symplectic automorphism group. So what does it mean symplectic? So symplectic, it means that it's fixed the holomorphic two forms. So for all G is the action of G on the holomorphic two form on S is holomorphic two form. So this is the holomorphic two form on S. So then, what I can do, so I can take S cross S, so this will be symplectic, but I will have two symplectic forms. So it will not be symplectic also. It will not be, yeah, it will be symplectic, but we'll have several holomorphic forms. Some of them will be degenerate. So to avoid this problem, we can quotient by the group. So actually, we have to quotient by some semi-direct product. So if here, sorry, I am going a little bit fast. It was actually for the one that was here last time. I just recall quickly. It's not the main objective of this talk. Okay, and then I can take some partial resolution. That I will denote like that. So yeah, so this is what we call the crescent resolution in codimension 2. So now I will explain a bit more. So crescent resolution, what is it? It means that the holomorphic 2 form here will be, in some sense, the holomorphic 2 form will still be non-degenerate. So crescent, here I can R. So I will have R tilde of the canonical bundle. This. I call this X. So the canonical bundle will still be. So the canonical bundle here. So this is what crescent means. Codimension 2, it means what? It means that this will not have any more singularity in codimension 2, but it can still have codimension, singularity in bigger codimension. So codimension singularities of this. Big equal or equal to 3. So this is the condition here. Okay. Yeah, and this always exists. So there is a theorem that says that this always exists in the projective case. So if you start with X, which is you start with X, which is symplectic, and which end projective, you can always perform a crescent resolution in codimension 2. Okay, so the singularities in codimension 2 can we always resolve such that you obtain something still symplectic for your resolution. Okay? So it's why I took this condition, bigger or equal to 4, because also when you are symplectic, you always have singularities in codimension even. You cannot have singularities in codimension 1 or 3. So the singularities are only in codimension even, and the singularities in codimension 2 can always be resolved. So it's why we choose. It's a good choice to make because we want something terminal. We want. This is the good things to study. This not because this has terminal singularity, and it's what we are looking for in the minimal model program. So this is the reason for this technical assumption. Okay, sorry for this, that was maybe not very precise because it was kind of reminder from my previous talk. Now I will really enter in the main topics of this talk, so I think I should be more precise. But yeah, do not hesitate if you have questions. So now I want to study what can we say about this primitively symplectic orbifolds. So last time I showed how to find example. Now I want to explain which condition expect, what are the limitations. And so one of them that can be nice to study, it's on the Betti numbers. So actually on the second Betti numbers. So there is the main theorem is the following. So it's a theorem with V foo. So if you take X, V, a primitively symplectic orbifold of dimension 4, then the second Betti number will be bound between 3 and 23. Okay, and moreover, if you have B2 equal to 23, then it's implied immediately that X, it's always implied that X is smooth. X is smooth. Okay, so this is. Okay. So actually, this is a generalization of a theorem that was existing already in the smooth case. So in the smooth case, it's a theorem of Beauville and One. And actually, in the smooth case, so example, for example, in the smooth case, we have very few examples. There is only 2 examples. So there is only B2 equal to 23 and B2 equal to 7. Okay, so there is here plenty of possibilities missing. So one of the questions is, can we do better? Can we do something better in the orbifold case? So also, can we find example for each Betti numbers in the orbifold case? So I will answer to this question at the end of my talk. Before, I want to give you a proof. So let's go for the proof. So there is 2 ingredients for the proof. There is first the theorem of Verbitsky. So Verbitsky theorem. I will call it. And the second ingredient, so the first ingredient is the Verbitsky theorem, and the second ingredient is just Riemann-Roch. So in the smooth case, we have Riemann-Roch, but in the orbifold case, it's more complicated. So I will have to give you the orbifold version of Riemann-Roch. So Verbitsky theorem that's following, it says that the symmetric product of H2 and XR is embedded inside the H4 of XR. Okay, so there is a natural map obtained by the cup product of intersection. And this is injected. Okay? So this is the Verbitsky theorem. So it's a first consequence, it's that B4 of X is bigger or equal to B2 of X times B2 of X plus 1. So it's one element to try to prove this inequality. But I think it will not be very practical to directly use the Betti number. You will understand why after that. Why it's not very practical to use the Betti number. It will be more practical to use the Hodge number. So I don't know if everyone knows what are the Hodge number. Maybe I should call a little bit. So the Hodge number, that's for example EHEG. This is the dimension. So well, this is not the definition. It's not property of HG, but well, it's a way to of omega EX. So this is the Hodge number. And there is the Hodge decomposition. So Hodge decomposition. For Kähler, so for Kähler manifold and also for Kähler orbifold. So the Hodge decomposition work also for Kähler orbifold, and it will give you the following: so that the bk of X will be equal to the sum from EG equal to K of the HEG.
I plus J equals to K, right?
Oh, sorry. we can rewrite this using the Hodge decomposition now. So before of x, it will be h04 plus h13 plus h22 plus h31 plus h40. Okay, but this will be always 1 because we have we're in the symplectic case, so this will be just the holomorphic 2-4 exterior square of 1. And this will be isomorphic, so the h13 will be isomorphic to the h11 in the symplectic case. So this will be h11. H2 is the same. This one also will be h11. Actually, it's always symmetric, so this one is always equal to this one. These are some properties about the Hodge numbers that are general. So these are general, that this one are the same. The fact that this is the same, it's only in the symplectic case. Okay, so we can rewrite this here. So we will have 2 plus 2 times h11 plus h22 that is bigger or equal to h11 plus 2 times h11 plus 2. This is our first equation that I will call stars. And yeah, so I said that this is the Betti theorem. So the Betti theorem was given in the smooth case. But actually, we are lucky because there is a generalization by Kähler in the singular case, so proposition. Kähler. Betti theorem is still true in the singular case. In the singular case, so for orbifolds in particular. So for our purpose, we can still use this equation. Okay, and so I told you that the second ingredient is the Riemann-Roch theorem. Riemann-Roch theorem. And it will be orbifold version of the Riemann-Roch theorem. So you know that the Riemann-Roch theorem is compute the Kähler characteristic of the vector bundle. So here we'll have to find something that looks like vector bundle, but in the context of orbifold. So it's what I will explain now. So an analog of vector bundle, but for orbifold. So we define what we will call locally V-free sheaf. So that F be a sheaf on X. F is said locally V-free if for all yeah, so for all X inside X, so there exists a local uniformizing system. So it was the data of U, V, G pi such that of x, so organizing system of x, and the free bundle, the free shift, F hat on V, such that G acts on this shift, and if I take the push forward, I will have a restriction of the bond of the sheaf on U. This is of the invariant part of sheaf. Okay. This is the locally V free sheaf. So what does it mean? It means that locally around X, it corresponds to a free sheaf. Sorry. It corresponds to a free sheaf downstairs.
And that V is different from that V.
Right?
The V that you have here is different from that V.
Beta.
The V. Local
The V.
The V.
V here?
Yeah, it's different from.
Here this is just the name.
Okay, and the notion of orbifold coincides with the notion of P manifold. Are you familiar with that notion? It's the same.
Yeah, it's the same.
Okay.
It's just, yeah, I don't know why. There was the old name and the recent name. Okay, but they are the same. Okay, so yeah, it's just locally, it's this. Okay, so locally here, it's more or less a free sheaf. So what's the meaning of locally V free sheaf? Okay, so now I'm ready to give you the version, the orbifold version of Riemann-Roch. So it's a generalization by Blasch, so it should be called the Blasch-Riemann-Roch theorem. So I still take X be a compact, so X here to be a compact Kähler orbifold with only isolated singularities. And F is a locally V free sheaf. Then, so there is the Euler characteristic of F. So the usual term that appear in a smooth case, so CH of F times the dot of X. But we will have a correction corresponding to the singularities. Like that. So here it will be a little bit technical, but I will explain what it means. So for each singularities, we consider one over gx. So here, yeah, maybe you will not understand immediately, but we will explain it. Yeah. Here I have that of G. Okay, so what does it mean, this term? So I consider U, V, Gx, and pi a local uniformizing system of X. So this is Gx. Gx, it's the G here of the local uniformizing system of X. Then what basically this. So if I take G of Gx, this acts on the tangent in 0 of V. Okay, so here I have action of Gx. So I can see G as a matrix on the tangent of V in 0. And actually it's symplectic, so I can see it as a matrix with a symplectic here, symplectic matrix, so in a good basis, we have just this eigenvalue. And we are in dimension 4 in what we want to do. Dimension 4, so this will be the action. We can see G like that. Okay, so if we consider here the determinant of E minus G, what is it? The determinant of E minus G is just the 1 minus lambda 1, the module square, and the module of 1 minus lambda 2 square, and this is strictly positive. Okay, so now I will explain what is this. So maybe I can erase here. So we also have G. X acts also on this part of a sheaf that I called F hat. So in particular, 0 is the point which is fixed by G, which is always the fixed point, that would correspond to the singularities inside X. So in particular, Gx acts on the fiber here in 0. And so it's provide actually a representation of G. So this gives a representation of G. That we called like X. But you will see it will be very concrete as it is here. It's not. It looks.
Can't we have just one of the lambda I is equal to 1? Can't we have just one of the lambda I equal to 1?
No, because we need that the singularity are isolated. So if one of the lambda will be equal to 1, we will not have isolated singularities, and then indeed the theorem doesn't work, because we will have 0 here and we have a problem. So no, it's forbidden. So, how much time do I have?
Actually, I don't know. I lost track.
I have all the time that I want. Very nice.
I can't remember when we started. I was just thinking about this.
Okay, so I can erase here maybe, or maybe here. Maybe I will erase here. Is it okay?
Maybe another 15, 20 minutes.
Okay, perfect. We'll erase here.
I'll take 15 minutes.
15 minutes. Very good. Maybe I will not give all the details then. Okay, so let's go. Let's try to apply this theorem. We first the first idea is to apply it for the simplest bundle that we can. So let's apply it for F is equal to OX. And see what we obtain. So Euler characteristic of OX is equal to. So here this will be 1, so there is only the top form. we'll have only tot 4 of x. And then the sum. So here the representation in this case will be just trivial representation. So we'll have sum of x, t of x, 1 over x. So it's long to write, 1 over the determinant. Okay, so this is what theorem gives for it, but this is what? So this is h 0 plus h01 plus h02 plus h03 plus h04 by definition. Oh no, sorry. There's a minus here. Minus. By definition of a characteristic, this is. Okay, but we are in the symplectic case. So in the symplectic case, the first chain class is 0. So as I explained with also I explained in the when I gave Bogomolov decomposition theorem. So symplectic orbifold are one particular case. So the first chain class will be 0. So this will be 0. So it's so simply connected. So this will be 0. This will be 0. And we have this is 1, and this we have only one holomorphic 2 form, so this is 1, and this is just also the product of holomorphic 2 form by itself, so this will be 3. Okay, so this gives us our first equation. Okay, now I will let's apply this theorem again, but with another bundle. Sorry, locally free sheaf. So we can apply it to, for example, omega 2 x. Yeah. So it's not, yeah, it's a little bit different than that. It's a push forward. So let's. With G, which is the inclusion. Okay, so let's apply for this. Maybe I can directly work here. So just directly change here. So here we have CH and Todes. So as I said before, the C1 will be 0 of x, and this will provide a lot of simplification. Okay, so this will be quite easy. So I will not give here all the detail, but it will be 2/3 of C4 plus 6 tot 4 of x. So it's simplified because the first chain class is 0. Okay, now what do we have here? So the trace. Let's see what is the trace. So here, this is just the exterior product. This can be seen as the exterior product of omega 1. Right. So, and yeah, I said before that the action of G is just lambda 1, bar, lambda 2, lambda 2 bar. And in some sense, it will be the dual of this, and then exterior product. So actually, the eigenvalue will just be the trace of omega x f. The eigenvalue will just be all the product here. So lambda 1 times lambda 1 bar plus lambda 1 times lambda 2 plus lambda 1 times lambda 2 bar plus lambda 1 bar times lambda 2 plus lambda 1 bar times lambda 2 bar, and just what is missing, lambda 2 bar. Also, I forgot maybe to say that since it's symplectic, this has to be 1. The module has to be 1. Okay, so here I have a module by just 1, and here I have 1. And you see that this is a real number because here and here I have if I make the sum here, I have 2 times the real part, and here also, so I have real numbers. So actually, this is bigger or smaller or equal to 6. Okay, all at module 1, so this is smaller or equal to 6. So what I can do is just here put instead an inequality and put a 6 here. Sorry, 6. Okay. But now I can use the equation that I had before. So if you remember, the equation that I had before, what was that? This, what was this here? What was this? So with the first equation, we have find this. Maybe I erase the key, or I need another color. But I will erase the key. So with the previous equation, we have 3 minus tot 4. X. But now these two also cancel. So we obtain, I will write just upstairs. My board is too small for what I want. Sorry. So yeah, these two concepts, so I obtain that Euler characteristic x is smaller or equal to 2/3 of C4, these two concepts, and so I have only 18. Okay, so this is equation. So this will be my equation 2. Can I write here? Okay, it's just missing one equation and then I will have finished. So it's a proposition of Blasch. So you know in the smooth case, you know that the Euler characteristic of x is just the C4 of x. So here there is a correction given by the singularities. Like that. I will call this S. And now we are ready to finish. Okay, so I can combine. Yeah. So here the Euler characteristic, I can also express it using the Hodge numbers. And I can combine these two equations. So this is the equation 3, and this is the equation 2. I combine the both, and I will obtain anything else. So combination of E2 and E3 give you 2H21 plus H22 smaller or equal to 64 plus 8H11 minus 2S. So this is S by definition. Okay, so we managed to take out C4 because we have C4 here and C4 here. So we managed to take out C4. C4 here and C4 here. And we obtain this equation. So here we are almost done. Now what can I do? S, it's always positive. Okay, you can see. And moreover, it's 0 only if it's smooth. So here, if we have something singular, we know that this is strictly smaller than 64 plus 8 H11. And here we know also that this is positive, it's a positive. So we have H22. And now, I only have to combine with the first equation. You remember the equation stars? So the equation stars was 2 plus 2H11 plus H22 equal to 3 plus H11 plus H11. So this was the equation stars. So I can combine the both to take out the H22. So I will have only an inequation on H2 on H1. Okay. And then we obtain the. I don't know if I need to explain this maybe. So here the H22 is smaller than that, so I can just rewrite 2 plus 2 H11 plus 64 plus 8 H11 is now equal to 3 plus H11 plus H11. Okay, now I just have an equation on H11, so I can just solve we obtain a polynomial of B2 and just it's implied like H11 has to be strictly smaller than, sorry, here it's of 21. And so the B2 is strictly smaller than 20.
There is no 2H11 there, right? Because it's 2, it's H21. Get rid of it. I see. Okay, right.
Yeah.
Okay. It's very similar. I'm sorry.
No problem. Yeah, it's a big thing. Yeah, so it's how we make it. So maybe now I still have 5 minutes. We will give some hint about the examples. Yeah.
Why is it smooth? Why is it smooth?
When B2 equal to 23.
Yeah.
So this is exactly the question. So you see that there is S here. So S is 0 only when X is smooth. So when X actually is smooth, so when S is smooth, everything is simple, and we will have an equality. We will have an equality, and no, so we will have here to be not strict, to be bigger or equal. And, yeah. So when it's singular, it has to be strictly bigger than 23. So when it's 23, necessarily it has to be small. S has to be equal to 0.
Excuse me. So you didn't discuss the other implication, so B2 greater or equal than something.
Ah,
Yeah. And
also good question. Yeah.
and I'm
So
a bit
this
surprised.
is,
So it cannot be 1.
No, so why it's at least 3? It's because we have the holomorphic 2 form. The holomorphic 2 form.
3. Okay.
Yeah, the holomorphic 2 form. Yeah, there is the real part and the imaginary part. So this gives you already 2, and then you have the Kähler class. So you 3.
And it's possible to find a orbifold for each value between 3 and
Exactly, it's what I am going to discuss now in the last 5 minutes. So the examples. So yeah, I think I cannot give you too much details, but at least I will give you the Betti number for which we have an example, and the Betti number for which we don't. So actually, from 3 to 16, from 3 to 16, we have examples. So yes, we have examples. Except for 30. And then there is 17 to 22, and here no, we don't have.
So this means that there are no examples whatsoever, or
We do not have example known. Sorry. So yeah, it's still an open question. Do we have example with Betti number 17 to 22, or is it impossible? Maybe it's impossible, and our theorem is not strong enough, so our bound is not sharp. We don't know. Also 13, it's not known, but maybe there is an example. We didn't manage to construct one yet. Okay, so yeah, I think I don't have time to explain you for each one how we construct the example. But you know, for some Betti numbers, we have only one example, but for some other Betti numbers, we have plenty of examples. For example, for Betti number 8, there is 9 examples, so 9 deformation class, for example. It's really depend on the Betti number. How easy is it? Okay, so I think I stop here. Thank you. Thank you, Grégoire.
any questions or comments? Grégoire?
Can you give us a hint of one example?
Sure. So yeah, I already gave this Fujiki construction, but there is other possibilities. So this Fujiki construction is really rich, provide many examples. For example, but there is other possibilities. Just taking some quotient. For example, if I take something which is deformation equivalent to K32, so an inverse scheme of 2 points on a K3, there is automorphism of order 11, symplectic of order 11. So this has been constructed by Mingardi. And it's have only isolated fixed points. So this will have only isolated singularity. So I do not need to do any resolution. It's already have codimension of a singularity bigger or equal to 4. So this is an example. And this has Betti number equal to 3. Yeah, so it's first Betti number. So these are the simplest example, just taking a quotient. Then there is other example with some resolution of singularities. And we can also, so some partial resolution. And we can also obtain example with moduli space of sheaves on K3 surface.
Could you project it?
Oh yeah, it's always, you can always choose projective stuff.
And you don't have Lefschetz theorem in these cases? You know, because Lefschetz theorem somehow is telling you how it has to be one, or in case that there exists Lefschetz theorem in this case.
I think there is Lefschetz theorem in this case, but I don't see why it has to be one.
Because H2 has to be an isomorphism, or P, or yeah, H2 has to be an isomorphism because it's 4-dimensional, right? So H2 has, it is projective, and if you have Lepsche's theorem, has to be an isomorph. Maybe I'm missing something.
H2 of P?
Pn has to coincide with H2 of, I'm missing something.
Strange. And maybe we can discuss later. But
Yeah, sure.
This would be a very high dimensional space. So
Okay, yeah, it doesn't have to be exactly a divisor.
No,
Right?
it's
So,
not.
yeah. I see.
More questions?
So for B2 to be equal to 23, you have those inequalities on the eigenvalues as well, right? They have to be very specific eigenvalues. I remember past simplification that you did in the trace in the numerator.
So yeah, because everything is smooth, so there is actually you can apply Riemann-Roch, normal Riemann-Roch. If we can apply normal Riemann-Roch, everything is more simple.
And do you have a bound on the number of singularities?
Very good question. Yeah, very good question. So yeah, we found 91. 91.
So that is multiplicity, that's the sum of the inertial groups, right? That's the sum of the GX, the orders of GX? Or?
No, I know, this is something else again. So no, this is really the number of singularities, so the number of the cardinal of singularities of X. It's have to be smaller or equal to 91. And if you want the cardinal of GX, you also compute a bound, but maybe not sharp at all. And also here, maybe it's absolutely not sharp. But I don't remember, unfortunately. But it was around 1,000.
Can that be achieved or?
Well, I think it's not sharp. I don't remember exactly. I don't remember the exact number, sorry. But we can have a look.
More questions? Let's thank Grégoire for this excellent.